Okay, so we're in section 3, chapter 2, and what these are applications of the product rule and the quotient rule. So this is so we can take the derivatives of objects, equations that consist of the multiplication or division of two functions. They don't have to be polynomials, but functions that we know how to take the derivatives of at this point. And all we know how to do is take the derivatives of the power rule, the polynomial, individual terms of the polynomial, and also sine, cosine, tangent, I think, some of the trig functions. Actually, I don't think we've done the tangent yet. No, we haven't, because we need to use the quotient rule to figure that one out. Okay, so let's just start. So we have problem number 2. 2 through 6 are just simple applications of the product rule. So this particular example consists of 2 polynomials. And you could multiply this out using the FOIL and then just do the individual terms, but what we're trying to do is prove that you can use the product rule as well. And one thing I tend to do is, if I have a product, and because we use f of x and g of x in the usual product rule definition, I'm just going to change the name of the function, because we can call it whatever we want to. And the reason I do that is so that I can be consistent about the result. So if I have h of x, which in this case is a product of 2 functions, f of x times g of x, where I'm going to say f of x is the first part, 6x plus 5, and g of x is the second part, which is x cubed minus 2. Actually, I think I'm going to put them like this so they're next to each other. So the product rule says that if I want the product of the derivative of the function, which consists of 2 terms which are multiplied together, you take the value of the function, you take the function, multiply it by the derivative of the second function. So this times the derivative of the second plus the derivative of the first function times the second function. So function, derivative, derivative, function. And so I'm going to move this down a little bit so I can write the derivatives right here above. We'll use blue for that. So then we just use the power rule and the rule that says that the sum of the derivatives, the derivative of the sum is the sum of the derivatives. So we look at this separately. The derivative of 6x is 6. And then we go down here. The derivative of 5 is 0. Here we have 3, the exponent, times x to the 2 power, which is 3 minus 1. The second term is 0. Its derivative of the second term is 0. So now, to find the derivative of the product, we just now plug in what we have. So it's just a matter of matching up. So you have 6x plus 5 times g prime of x, which is 3x squared. And then you do the second part, f prime of x, which is 6, times g of x, which is x cubed minus 2. So that's the answer. We usually want to simplify things, so we multiply everything out using the distributed property. So 3 times 8 is 16. X times x squared is x cubed. Then we do the second term, so we get 15x squared. So that's this part. Then we add the second part, so let's go ahead and multiply that out. And that's easy because it's just a constant times each term. And then we look for like terms and combine those. So we have x cubed and x cubed. So it gives us 24x cubed plus 15x squared minus 12, and that's the derivative. Now I'm going to prove that if we multiplied it out, we get the same result. You don't need to do this for the problem, but I'm going to use FOIL here. So if we multiply it out, we'll get 6x to the 4th plus 5x cubed minus 12x, this times that, minus 10. So that's just FOIL. And so then to take the derivative, we just take the derivative of each term separately. So you'll have 4 times 6, which is 24. Reduce the exponent by 1. 3 times 5 is 15. Reduce the exponent by 1. The exponent is 1 here, so 1 times 12, negative 12 is negative 12. The derivative of x is 1, so that's the answer. And we go to the other page, and you can see that they're exactly the same. Problem number 4. G of s is the square root of s times the quantity 4 minus s squared. So again, I'm going to just go ahead and change the name of the variable. And then I'll call the first term the square root of s. The second term, g of s is the second term in the product. So g of s is 4 minus s squared. If you multiply g of s times f of s times g of s, you get h of s. So we take the derivatives, and what we're going to do is anytime we have a square root, we write it as a fractional exponent. So you get s to the 1/2 power. And now it becomes a form of x to the n, where n is 1/2. So you take the exponent, multiply it by the term, reduce the exponent by 1. So 1/2 minus 1 is negative 1/2. G prime of s is, well, that's the derivative of 4 is 0, and then you go negative sign to s. So h prime of s is f prime of s times g of s plus f of s times g prime of s. So now we just plug in, so we have 1/2 s to the minus 1/2 times 4 minus s squared. So that's the first part. The second part is f of s, which is, I'll just put the square root of s, square root of s times that, which is negative 2s. And then we just kind of clean it up a little bit. So maybe I shouldn't have done the square root. Let me just write it as s to the 1/2 power, because that'll help. So I'm just using this version here. Okay, so we're going to multiply everything out and then simplify. So we get 1/2 times 4 times s to the minus 1/2 power. The second term, this times that, we'll get 1/2 s to the minus 1/2 times s squared. I'm going to take the negative sign, put that up front. We get s to the 1/2 times, not s, not 2, s. Okay, so you get s to the 1/2 times negative 1 times s. Okay, properties of exponents. We don't like to have negative exponents, so we move that to the denominator and make it positive. So it becomes positive 1/2 in the denominator. We multiply these two things together, so we'll get 2 divided by s to the positive 1/2. The second term is negative 1/2, and then you add the exponents if you have the same base, which we do. The base is the variable s. So 2 plus a negative 1/2 is going to be 3/2. And then here we add them. And remember, we have an exponent of 1 there. So 1 plus 1/2 is also 3/2. So we get plus, or it's minus, sorry. So you get minus s to the 3/2. And then one more step here, we can change this to, anytime we have something this half power, we change to the square root. And then you have minus 1/2 minus 1, so you'll get minus 3/2. And we just leave this as s to the 3/2. We don't. Another way of writing would be the square root of s cubed. Let's just write that just to show you what it is. You could say it's the square root of s cubed. That would be the same thing. Okay, so that's our answer. Now I'm going to go back and just use, if you multiply things out, the original function, if you just use the distributive property to multiply things out, you get 4 times the square root of s minus, okay, you got a s to the 1/2 times s to the 2, so you get s to the 5/2. And that's bothering me here. It may have been a mistake, so the constant's not going to be the same. So we'll go back and figure out. Let me make sure I didn't make any mistakes here. Okay, so if you take s h prime of s, the derivative of this is 1/2 s to the minus 1/2. We've already done that. And the second one is you take the exponent and you reduce the exponent by 1. 4 divided by 2 is 2, and s to the minus 1/2 power is 1 over the square root of s, and so we get 5/2 s to the 3/2. Okay, so which doesn't match up with this, so where did that go wrong? So I'm going to move this up here so I can follow my logic. Oh, I forgot the 2. There we go. So this should be a 2 there. So that should be a 2 there. So I get that's 5/2. Okay, so now they do match. If I go here, you can see I got, oh, I don't know why I did X there. Fix that, sorry. Anyway, now it looks 2 over the square root of s minus 5/2 s to the 3/2. Okay, so that's good, I checked. Problem number 6. G of x is equal to the square root of x times the sine of x. So these are 2 terms. Again, you don't need to do this, but just makes it easier to follow. So what we can say is that in this case f of x is the square root of x, which is equal to x to the 1/2 power. G of x is equal to the sine of x. So we take the derivatives. We get 1/2 x to the minus 1/2. And when we take the derivative of the sine, it's just the cosine. You just have to know that or look it up in the book. And we can rewrite this as 1 over 2 square root of x. You see this a lot. So at some point you may just say, oh yeah, the derivative of x to the 1/2 power is 1 over 2 square root of x. Okay, so the derivative of this composite function, you just kind of like cross multiply these terms. So we'll get 1/2 x, well, I simplified it and then I didn't do it. Okay. So 1 over 2 square root of x times sine of x plus the original one, which is the square root of x. Let's use that. I don't have to put it to 1/2 power times the cosine of x. And there's really not a whole lot you can do to simplify that. You could factor out, the only thing you could do is say factor out 1 over 2 square root of x, and then you'd have the sine of x. And the second term, to do this, you would multiply the numerator and the denominator by 2 square root of x divided by 2 square root of x, and actually no, you have to, ultimately the answer is 2x cosine of x. Okay, see if I multiply this times that. 2 divided by 2 is 1. X divided by the square root of x is the square root of x. Now, is that any better? I don't know. So this will be fine. Okay, we're on number 8. You can see we're doing all the even problems, which means the answers are not in the back of the book. Okay, so the next couple, which are all the even ones in the next section, are the quotient rule. So a lot of times the quotient rule, it's hard to simplify it once you get done. So it's just a matter of, again, I'm going to rewrite it, call it h of t, so that I can use the quotient rule. And as I'll write it down for this first problem, but the quotient rule, say h of t, where h of t is the quotient of two functions. So h of t is equal to f of t, in this case, divided by g of t. So this would be f of t, this would be g of t. So if you take the derivative, you can use the quotient rule, which says that, and I always forget which one comes first, and how do I remember it? Because it's the same kind of thing except as the product rule, except there's a subtraction involved. And I think, if I remember it correctly, I'll have to just check, but I think the first term involves the derivative of the numerator. Then you multiply it by the denominator, and then you subtract the other one, g prime of t. So you switch those. If I put a plus here, it would be the product rule, but then you divide it by g of t squared. That's not the hard part. So I'm actually going to have to look, because I don't know why I have a mental problem with this. Yeah, okay, so this is correct. The book has this one first, but it doesn't matter. Okay, so that's the quotient rule. So basically you just do what we did previously. You write down f of t, which is the numerator. You write down g of t, which is the denominator. Then you take the derivatives, just using the rules that we know. Since these are polynomials. Derivative of t squared is 2t, derivative of 2 is 0, derivative of 2t is just 2, because the derivative of t is 1, so you get 2 times 1. That goes to 0, and then you just plug it in. So f prime of t times g of t minus f of t times g prime of t, all divided by g of t squared. So we can simplify the numerator just by multiplying stuff out and combine like terms. So you get 4t squared minus 14t, these two, then you would get negative t squared times 2, so negative 2t squared. Then you get negative 2 times 2, negative 4, all divided by 2t minus 7 squared. And then finally, the final answer here, combine like terms, so you get 4t minus 2t, which is 2t squared, minus 14t minus 4, all divided by 2t minus 7 quantity squared. Now, say I forgot this. I forgot the quotient rule. Could I do this using the product rule? Well, the answer is yes, because you could rewrite this original quotient as a product. What you would have to do is you'd take g of t and you'd raise it to the minus 1 power. So then this is a product. Now you have to use a rule that we learned in the next section, the chain rule, to evaluate that derivative. But anyway, that's just a extra bit. Number 10. So we're lucky here because it's already started out with h, so I didn't have to rewrite it as that. But so we have a quotient. In the numerator, we're going to call f of s. The denominator we'll call g of s. And so just like before, we take the derivative of each term. That one's easy. Derivative of s is just 1. The derivative of the square root of s, remember it's 1/2 1 over the square root of s. Change that to s to the 1/2. Get that. When you take the derivative, you get s to the minus 1/2, which then you can move to the denominator. And the second constant part goes to 0. So h prime of s is equal to f prime of s times g of s minus f of s times g prime of s. All divided by g of s quantity squared. F prime of s times g of s minus f of s times g prime of s divided by g of s quantity squared. Again, we can simplify the numerator somewhat. So we have the square root of s minus 1. Multiply that out. And then we have s divided by the square root of s. Okay, that's s to the first power divided by s to the 1/2 power. So you subtract this exponent from that exponent. You just write it out. So what we're having is s to the first power divided by s to the 1/2 power. In this case, you take this exponent, subtract that exponent, so you'll get s to the 1/2 power. So this becomes negative 1/2, which s to the 1/2 power is the square root of s. So you get the square root of s, whole thing divided by square root of s minus 1 squared. So we can combine these two. So we'll get 1/2 times the square root of s minus 1 divided by the square root of s minus 1 quantity squared. Number 12. Kind of like the last one in the last section. This one involves a trig function. Again, I'm just going to change the name. Probably in the test, I'll just call them all h of s or h of x or something like that, or h of t, so you don't have to make that change. But okay, so the numerator we're going to call f of t. The denominator we're going to call g of t. I almost put 1 over t cubed, but that wasn't right. Okay. So the derivative of the cosine is negative the sine. That's in the book. G prime of t using the power rule is 3t squared. So the derivative of the composite function here is, okay, we take f prime of t times g of t, so we get negative sine of t times t cubed minus f of t times g prime of t, all divided by g of t squared. And in this case, there's not a whole lot that we can do. We could, we got t squared, t cubed, and we got t, so we can actually divide by t. If we divide everything by t squared, the first term, t squared, t cubed divided by t squared is going to be t. So we have negative t sine of t. So that's this term. The second one is negative, t squared is going to cancel out, so you get negative 3 cosine of t. And then this is t to the 6th. So there you multiply the exponents. When you raise an exponential function to a power, you multiply the exponents together. So this is 6, but I'm canceling out 2 of them, so it'll be t to the 4th power. We probably talked about this in class, but remember, this is some L of t. If you have a negative sign, you put that out in front when you simplify something. Then you put a constant. Then you do any polynomial part. And then finally you put the other ones, which would be like trig functions. So if I originally had L of t as being something like the sine of t times negative 4x cubed, I would simplify this by bringing the negative all the way to the front, then put the constant next, then put the polynomial next, and then put the trigonometric or exponential logarithmic functions last. That's just kind of the order that typically people put it in. One of the reasons is if you rewrote this as it was negative 4 sine of t x cubed, it would be hard. So is it the sine of that, or is it the sine of t times x cubed? So by doing it this way, there's less confusion about where everything is. To be clear, if you did it this way, the second way, you would have to say something like, you'd have to put the sine of t in parentheses and then put x cubed afterwards to make sure that we were clear on what was the argument in the sine function. Okay, the next two problems, there's not a whole lot of difference between what we've been doing, what's in the new one. Basically, you do the same thing for the first part. You find f prime of x, then you just find f prime of c. You just plug the number into the expression that you got from the first part. So it's not rocket surgery. So 13, f of x is equal to x cubed minus 3x quantity times x 2x squared plus 3x plus 5. Again, let's just call this h of x. And again, you don't have, if you feel comfortable just doing this in your head, don't feel like you have to write this whole thing out. So what do I mean by that? I'll explain in just a second. So those are the two terms in the product. So we take the derivatives, use the power rule for each term. Okay. Hopefully at this point you're feeling more comfortable. So h prime of x is, using the power rule, you just cross multiply and add them together. So you get x cubed minus 3x times g prime of x, 4x plus 3. The second term is this direction. So you get 3x squared minus 3 times this term, 2x squared plus 3x plus 5, close parentheses. So that's the derivative. And in this case, I don't think I'm going to actually simplify it, just because it's going to be, well, let's just do it. If you don't want to simplify, just plug the numbers in. So if you wanted to get the value at c equals 1, you just plug 1 in. So we'll do that, and then we'll do it the other way. So if I said h prime of 1, that means plug in 1. So you'd have 1 cubed minus 3 times 1 for this first term. You'd have 4 times 1 plus 3. The second term would be 3 times 1 squared minus 3. 2 times 1 squared plus 3 times 1 plus 5. Then you just work it out. Well, that part's 0. So this whole second thing has to be 0. And then the first part, we're just going to have 1 minus 3, which is negative 2. And the second part, you're going to have 4 plus 3, which is 7. As I said, the second thing is 0 because that part's 0. And so you get negative 14. So that's actually f of f prime of c. Now we're going to do it, multiply it out, simplify things. So what do we get? Using FOIL, 4x to the 4th minus 12x squared plus 3x cubed minus 9x. Okay, so that's for the first one. The second one, got more terms. So FOIL, when you have extra terms, just take this times that, this times that, this times that. And then you take this times that, this times that, this times that. So we're going to end up with 6 terms. So 3x squared times 2x squared is 6x to the 4th. The next term would be 9x cubed. And the next term would be 15x squared. This times that, this times that, this times that. Okay, the next one is negative 6x squared. So we're taking negative 3 times that. And we just continue on, negative 9x minus 15. So those are all the 3 terms. This multiplied out using FOIL, this multiplied out by using each term. And then we simplify it by combining like terms. So we've got 4 and 6. So we have 10x to the 4th. X cubed, we have 3 and 9 plus 12x cubed. 3 and 9 is 12. Negative 12 plus 15 minus 6. So that's negative 18. So we get negative 3x squared. 3 minus, okay, that's right. Then we go to x. So we got negative 9 again, so that's negative 18x. And then we have the constant. Negative 15. Hopefully I got that right. Let's see. 6 plus 4 is 10. Negative 3 plus 9 is 12. Negative 12 plus 15 is positive 3. Minus 6 is negative 3. Negative 9 plus negative 9 is negative 18. Negative 15. Okay. So now if we stick 1 in there, we're going to get 10 plus 12 minus 3 minus 18 minus 15, because all these 1 to any power is 1. So that's 22. 22 minus 3 is 19. Minus 18 is 1. 1 minus 14 is negative. 1 minus 15 is negative 14. So hopefully that's what we got previously. It is good. Okay, so we got the same answer. So whichever way you want to do it's fine. 15. So this is the same kind of deal, except we're doing using the quotient rule. Again, for convenience. Okay, so let's say f of x is the numerator, g of x is the denominator. Take the derivatives using the power rule. So those are the derivatives. Therefore, h prime of x is f prime of x times g of x minus f of x times g prime of x, all divided by g of x quantity squared. I'm going to go ahead and simplify the numerator just because it's not that hard. So we multiply it out. You get 2x squared minus 6x from this, and then you would get negative x squared plus 4 from this. Negative x times 1, and negative times a negative is positive, all divided by x minus 3 quantity squared, and then combine like terms, so we get x squared minus 6x plus 4, because 2 minus 1 is 1. Get that. So that's h prime of x. Then what we're looking for is at c equals 1. Like c. Oh, c. So we're going to put. So what we want is h prime of 1. Okay. So we get 1 squared minus 6 times 1 plus 4 in the numerator, 1 minus 3 in the denominator. You do the math. 1 minus 6 plus 4, so that's 5 minus 6 is negative 1. And in the denominator we get negative 2, so the answer is 1/2. So that is the value of the derivative at x equals c, where c is equal to 1. Again, that's the slope of the tangent line at that particular point. Okay, so we're moving on. The next two problems are the case where you think you might have used the quotient rule, but you don't. So you just have to be careful. I mean, you could use the quotient rule, but you don't need to. So you'd see this expression, and you say, oh, I got a quotient, so I need use the quotient rule. But the point here is that if you rewrite this, and you take the term that's in the denominator, move it to the numerator, then all you have is a constant times a polynomial. So you rewrite it, then you differentiate it. So the constant stays there. You have the exponent, which is negative 2, and you raise that to the exponent minus 1. So negative 2 minus 1 is negative 3. Then you simplify by multiplying things out. So you get negative 14 thirds. 2 times 7 is 14. And then you would move this to the denominator. Now you could have used the quotient rule, so let's just prove that this is true. And some people do this not to prove that it's true because they forget to do this part. They go, oh, it's still a quotient. So what they do is they say f of x is equal to 7, g of x is equal to 3x squared. So then you use the quotient rule, and you get 0 for f prime of x. G prime of x is 6x. So the quotient rule would say h prime of x is this times that minus this times that all divided by g of x, which is 3x quantity squared. Okay, then we simplify it. Okay, first term is 0, so you get negative 42x in the denominator. Okay, so here's the rule people forget. When you have a product and you raise it to a power, you take each term, raise it to the power, and then, so it's kind of like the exponent or product is the product of the exponents by themselves. So what does that mean? It means that we take 3 squared, and then we also take x squared squared. So we do each one of those separately. So negative 42 x divided by 9 x to the 4th. And can we simplify? Is there a common denominator or common factor? Well, there is. 42 can be divided by 3, 9 can be divided by 3. So 42 divided by 3 is 14. 9 divided by 3 is 3. And then you have x divided by x to the 4th, so you can cancel out one of those x's. So the numerator becomes, this part becomes 1, this becomes x cubed. So we get negative 14 over 3x cubed, which should be the same answer we got here. Negative 14 thirds. Okay, so we got the same answer. So you can use the quotient rule, but I think this was easier. So there's no point in doing it if you don't have to. Just rewrite it. Okay, so this is a second example of rewriting something or simplifying it. So there's actually two. Well, this actually is just simplifying it because, again, you might look at this and say, oh, I got a quotient, so I used the quotient rule. But the first case was where we just had to rewrite it and move the variable term to the numerator and change the sign. In this case, all we have to do is just simplify it because we've got x to the 3 halves. So when you take 3 halves and subtract 1, you get 1/2. So these are equivalent. As far as one thing that's different is, of course, this function would be undefined or indeterminate at x equals 0, whereas this one is not. So that's one thing you have to be careful about. So let me just reiterate what I'm saying there. So if I said, what is the domain of this function? I would say it's from negative infinity to positive infinity, except x cannot equal 0. Because when x equals 0, then it's indeterminate. Whereas this domain, you can see I can stick any number in there. Oh, also, actually, it doesn't go. You have, it would be actually from 0. It would actually not, that would be, x would have to be greater than 0. Why did I do that? Because I can't, this is the square root of x cubed. And you can't take the square root of a negative number. So this would be not including 0, whereas the second one, it would include 0. So there's a slight difference in the domain. Maybe you're not convinced that you can't have x equals 0 in here, or x less than 0. You can't have x less than 0 here for sure. But how about x to the 3 halves power? Well, you can rewrite, you could either write that as the square root of x cubed, or you could write it as x to the 1/2 power cubed. Either ways. Okay. So, or the square root of x, well, let's write it as that, square root of x cubed, where you can take square root of x quantity cubed, or you can take the square root of the quantity x cubed, same thing. And you can see in this case, I can't have a negative argument because that would give me a negative square root. Here, if I have a negative number, if you cube a negative number, you still have a negative number. So it doesn't get rid of the negative numbers. Either way, either one of these cannot be less than 0, and then it can't be 0 because it would be indeterminate. Okay, so every place except x equals 0, this works out good. So then now you can take the derivative, and you would say y prime is 4 times 1/2 times x to the minus 1/2 power. That's the derivative. So you get y prime is equal to 2 over x to the 1/2, positive 1/2, which is 2 divided by the square root of x. So that would be the derivative. Okay, this is problem 34. Section 2, pardon me, Chapter 2, Section 3. So we have that g of x is equal to x squared times 2 over x minus 1 over x plus 1. Now you might be tempted to use the product rule or the quotient rule, but I think what they want us to do is to find the common denominator for these two terms. So you have 2 times x plus 1 minus x, all divided by x times x plus 1. So what I've done there is I've cross-multiplied because I have two fractions. So you get 2 times x plus 1, x times minus 1. You divide by the product of the two denominators. And you'll notice that I have x here and I have 1x there, so I can cancel those out. And so let's see what we have. We'll have 1 left x left over. Inside the parentheses, we'll have 2x plus 2 from this, expanding that out, then subtract x and divide by x plus 1. And so I'll have x, 2x minus 1x is 1x. So we get x plus 2 over, so we get x times x plus 2, and we'll go ahead and multiply the numerator out completely. So we'll get x squared plus 2x divided by x plus 1. And now we can use the quotient rule. So let me just call h of x the function. So I'm rewriting that so that I can use f of x and g of x to represent the numerator and the denominator. So the numerator is f of x, and g of x now is going to be the denominator. So I take the derivative, so I get 2x plus 2 over here, and I get just 1. So the product, the quotient rule, so this is h prime of x. If h of x is made up of the ratio of f of x and g of x. So we'll go look up the quotient rule. And it says it is, this is on page 121, g of x times f prime of x minus f of x times g prime of x, all divided by g of x, quantity squared. So now all I have to do is just plug in what we have. So g of x is 1. No, that's g prime of x, sorry. G of x is x plus 1. F prime of x is 2x plus 2. And then we subtract f of x, which is x squared minus 2x, multiplied by g prime of x, which is 1. And we divide by g of x squared. So we'll multiply out all the terms in the numerator using FOIL. So using FOIL on that, I get that, and then the last two terms will distribute the negative sign. So they change sign. This becomes negative x squared. This becomes positive 2x. And that's all divided by x plus 1 squared. So now we'll simplify. So we have 2x squared minus 1x squared. That gives us x squared. We have 2x plus 2x plus 2x, which is 6x. And we have 2 as a constant, all divided by x plus 1, quantity squared. And we can't factor the numerator and get a nice factor, so we will say that's as simplified as we get. So I'm just checking the solution out here. See what the answer is. So this is problem 34, I think. Section 2.3, number 34. So let's see what they do. They didn't get the same answer I did. They did it slightly differently. So let me go back and see what I did wrong. They've got x squared plus 2x plus 2. Do I have a sign wrong somewhere here? Oh, here it is. That should be plus 2, which makes this negative 2, which makes this into 2x. So what they actually did, let me just go back and explain how they did it. Got the same answer, but so they just multiplied it out without finding a common denominator. So you end up with 2x squared over x minus x squared over x plus 1. And if you simplify the first term, you cancel that out with one of those, and you get 2x minus x squared over x plus 1. So then they took the derivative, and they used the quotient rule for that. On this one, and they just did the derivative of 2x, which is 2 there, and then they found a common denominator. So I think mine was probably just as easy as theirs was. So again, the answer, final answer you should have gotten is x squared plus 2x plus 2 over the quantity x plus 1 quantity squared. Okay, this is problem 42. So it's section 2-3, number 42. So this is just using the quotient rule. So again, I'm going to just call this h of x to make it fit into my previously defined system of solving these problems. So my numerator is f of x, my denominator is g of x. So I take the derivative of the sine, I get the cosine. I take the derivative of x, I get 1. So it says that the derivative of a quotient is equal to f, see if I can remember this, g of x times f prime of x minus f of x times g prime of x divided by g of x quantity squared. So once I have these, I just make sure I do the right ones first, which would be this cross. So I get h prime of x is x cosine of x, and then I subtract f of x, which is sine of x, times the derivative of g of x, g prime of x, which is 1, and I divide that all by g of x squared. And that's about it. The only thing we do is we could get rid of the 1. And I can get rid of the parentheses. So that's number 42. Let me just check it out. X cosine of x minus sine of x over x squared. Okay. Okay, we're on our second group of problems here. So we're on problem 43. And we're just dealing with derivatives of a yep. Okay. Just see what we have here. So actually, this one we don't actually have to use the product rule. Well, we have to use the result of the product rule. So the result of the product rule was that, or the quotient rule is the derivative of the tangent was secant squared, but we don't actually have to use the product rule here because we're adding stuff together. So it's simply the derivatives derivative of the sum of the two terms is the sum of the derivatives. The derivative of x is 1, so we get -1, and the derivative of the tangent of x is equal to the secant squared of x. And I was just thinking, you could simplify that. Remember, again, I never remember this, so I have to do it from what I do remember. So that's the Pythagorean identity. And we want to get the secant version, so we want to divide by the cosine. So we get cosine divided by the cosine divided by the cosine squared, of course. So this becomes tangent, sine over cosine is tangent, plus 1 is equal to secant squared. So if we try to get what we have up here, if we subtract secant from both sides, well, no, actually subtract 1 from both sides, so you'll get tangent squared of x is equal to -1 plus the secant squared of x, and so that's equal to the tangent squared of x. So we could actually say, we could use trig substitution, trig identities here to give the answer as the tangent squared of x. So that's interesting. And we'll later on probably figure out why that's the case. But anyway, yeah, when we integrate stuff, we'll see that how this relationship makes sense. But it still makes sense. This is a result. I would be okay with that. But while we're at it, let's go ahead and simplify it. Number 46. So we have g of t is equal to the 4th root of t plus 8 secant of t. Again, we're not going to use the product rule. You might think we have a product here, but we actually use the constant multiplier rule. So we just take 8 times the derivative of that. We will use use the quotient rule to figure out what the derivative of the secant is, but I'm just looking it up in the book here somewhere. Well, I'm sure we did that. Let's see. Oh, there they are, page 123. I knew they were in that section. So we know the derivative of the secant is secant tangent. So what we're going to do first is we're going to rewrite the original expression as changing the 4th root to t to the 1/4. Second term just stays the same. Then we take the derivative, so s prime of t. So our exponent is 1/4, so we bring that down as the multiplier. And then we have t, and we subtract 1 from 1/4. 1 from 1/4, so you get -3/4. The second part, you have the constant multiplied by the derivative of the secant, which is the secant of t times the tangent of t. And finally, we clean it up a little bit because we have a negative exponent. So what we'll have is 1/4 t to the 3/4 plus 8 secant t tangent of t. And the only other thing, you could rewrite that first term as 4, let's see, it'd be the 4th root of t cubed. Second term doesn't change any. Okay, this is problem 46, chapter 2, section 3. So we have h of s is equal to 1/s minus 10 times the cosecant of s. So we really have a application of the addition rule. And all we really have to do is rewrite this as 1/s is s to minus 1 power. The rest of it is just using the tables. We don't have to combine these two into a common denominator, anything like that. So when we take the derivative of s to the minus 1, you get negative 1 s to the minus 2. And the derivative of the cosecant is the cosecant, it's actually negative. So if you go to the book, you'll see it's negative the cosecant of s times the cotangent of s. So I rewrite this as SO 1 over s squared. You get the negative sign, so you get negative 1 over s squared, and the negatives cancel out here, so you get positive 10 cosecant of s times cotangent of s. And that's problem number 46. Let me just check the answer. Negative 1 over s squared plus 10 cosecant s cotangent s. Okay, this is problem 51. So we got f of x equals x squared tangent of x. So we've got a product of two terms. We could rename this h of x just for convenience sake. Doesn't matter what it's called. And we'll call f of x the first part of the product and g of x the second part of the product. And then we take the derivative of each one. So this is an exponential. So derivative of x to the n is n times x to the n minus 1. Here we have a trig function, and the derivative of the tangent from the table is secant squared. So h prime of x is going to be f of x times g prime of x plus g of x times f prime of x. So you see I've got f of x, g prime, g, f prime. So we take f of x times g prime of x plus g of x, which is tangent x times f prime of x, and then we just clean it up a little bit. So this we can take away the parentheses, put the polynomial first, which it already is. Here we're going to take the parentheses away and move the constant to the front, then the polynomial, then the trig function. And that's your answer. So that's it. So now what we're doing is we're moving on to a couple of word problems. Of course, everybody freaks out about that, but so all we're going to do is they're going to give you expressions. Something is a function of some dependent variable, a function of some independent variable. In problem 87, the independent variable is time, t. So you get this function that predicts the growth of bacteria, and it's represented by this expression that's kind of like a rational expression. So there's a couple of ways you can handle this. Right now, you could say, well, I have this times that, and then you'd have to apply the quotient rule at that point. You could multiply the 500 out and then take the derivative of the separate things and use the quotient rule there, and that's what I'm going to do. There's more than one way to skin a cat here, but if we multiplied 500 times each term, you'd have 500 times 1 is 500, 500 times 4 is 2,000, so 2,000 t divided by 50 plus t squared. So now we take the derivative. So the derivative of a sum is just the sum of the derivatives. The derivative of this part is 0 because it's a constant. So to find the derivative of this expression, basically we have to take the derivative of that. So let's just go ahead and write it out. Let's let the numerator be 2,000 t and the denominator to be g of t. So we get 50 plus t squared. Now, so the quotient rule, we just have to find out what f prime of t is, which is just 2,000. 2,000 times the derivative of t is 1. g prime of t, we have the derivative of 50, which is 0, plus the derivative of t squared, which is 2t. So let's just get rid of the 0. And the quotient rule, what we're going to do is the quotient of this p of t is the quotient. We're just taking this part here. So remember what it is. I always forget which one it is. I think it's f prime of t times g of t minus, and then we switch them. So it would be g prime of t times f of t, all divided by g of t quantity squared. So let me just plug stuff in. So f prime of t is 2000. G of t is 50 plus t squared. G prime of t is 2t times f of t, which is 2000 t, all divided by g of t, which is 50 plus t squared quantity squared. So g of t is that, and we square it. Okay, so that's the answer. So that's p prime of t. If we can simplify it, we should. In this case, we can simplify it by multiplying everything out in the numerator. So 2,000 times 50, 2,000 times 50 is 100,000. And then we get plus 2,000 t squared. And here we get minus 2 times t is t squared, and we get negative 2 times 2,000, so it's negative 4,000 t squared, all divided by 50 plus t squared squared. And then we combine these two last terms. So p prime of t is 100,000 minus 2,000 t squared, all divided by 50 plus t squared quantity squared. And it says find the rate at which the population is growing when t equals 2. So all we know is just plug in 2 for t. So we'll get 100,000 minus 2,000 times t squared, all divided by 50 plus 2 squared quantity squared. And they get that in the calculator. So 100,000 minus 2,000 times 4, it's 92,000, divided by 50 plus 4 quantity squared. And so when we do that, we get 31.6. And what are the units? Hours. So the units of this would be bacteria per hour, as far as the units are concerned. And I'm just going to check the answer before we go on. Okay, so I checked the book, so my answer book, excuse me, and that's the correct answer. So it says, when satellites observe Earth, they can scan only parts of the Earth's surface. Some satellites have sensors that can measure the angle theta shown in the figure. Let H represent the satellite's distance from the Earth's surface, and let R represent the Earth's radius. Let me just draw a picture. It's kind of like what they have. So you've got some point here in space. And then you have this, which goes tangent to the circle. And then you have your radius right there. And then if we go straight from the center of the Earth to there, we have that. And so this is the angle theta. This distance here is the height above the Earth's surface. this is the radius, and this little bit here is the radius. So those are both the radius of the Earth. And it says show that h equals r cosecant of theta minus 1. So what you probably would do is, we have a right triangle here. Okay, the tangent line is perpendicular to the radius. So given this is a right triangle, what we can do is this is our hypotenuse and this is our radius. This is our opposite side, opposite hypotenuse, and that's the angle theta. So we could use the sine of the angle theta. So you'd say the sine of theta is equal to the opposite length divided by the hypotenuse, which is r plus h. Now if we want to solve for h, we could multiply both sides by r plus h, and we get r plus h times the sine of theta, and that's equal to r. And we multiply out, so we get r sine of theta plus h sine of theta is equal to r. Again, we're trying to solve for h, so we're going to move this term to the other side. So we'll get r minus r sine of theta. This goes over there, it becomes negative. And then we divide both sides by the sine of theta. So we'll get r minus r sine of theta divided by the sine of theta. So we factor out r. We get r times 1 minus the sine of theta divided by the sine of theta. And if we, instead of having a common denominator, if we have 1 over this, what we get basically is 1 over the sine of theta minus the sine of theta over the sine of theta. So that's the answer. R cosecant of theta minus 1. And that's because 1 over the sine of theta is cosecant, just from the definition of cosecant. Okay, find a rate at which h changes with respect to theta when theta equals 30 degrees. So you find you have to take the derivative. So h prime is basically the rate of change of h with respect to theta. R is a constant in this case. It's going to be the radius of the Earth or whatever you're rotating around. So the variable is theta and h. So this is our independent variable. And this is our dependent variable. So you just take the derivative. So we would take dh d theta, or we could say that's h prime. And this is so what we do here? Well, I would multiply it out. So you'd have r cosecant of theta minus r. R is a constant. So the second term goes to 0 when we take the derivative of it, minus just the derivative of constant is 0. Here we have a product, but it's not a product. It's actually just a constant times. This is the only part we have to worry about. So we'll get r times the derivative of the cosecant of theta. So we go to the book, page 123. The derivative of the cosecant is negative the cosecant of theta times the cotangent of theta. So that's the derivative. And then we want to evaluate that at theta equals some value, which I'm going to look in the book again, is 30 degrees. So we basically, the radius is 3960, and you have minus the cosecant of 30 degrees times the cotangent of 30 degrees. Now, we don't have cosecant in our calculator, but we do have we do have sine, so this is really negative, and then we'll have 1 over the sine of theta, or 1 over the sine of 30 degrees. So that's the cosecant part. And then we'd have 1 over the tangent of 30 degrees. And you multiply that out. So you could do that by just plugging in to your calculator, make sure it's in degrees. But we're going to do that, but what we know is we know that the sine of 30 degrees is equal to 1/2 from our unit circle, or from just remembering it. So remember, the unit circle looks like this. 30 degrees is right there. So the y value is equal to the sine of theta, and the x value is equal to the cosine of theta. So if I look at the y value, it's about halfway up. So that's where I get the half from. Now the tangent of 30 degrees is sine of 30 degrees divided by the cosine of 30 degrees. We already got the sine, which is 1/2. The cosine is always the other one. So the other side is square root of 3 over 2. So the cosine of 30 would be the square root of 3 over 2. 45, they're both the same, square root of 2 over 2. Okay, now what is that? 1/2. I'm going to take the reciprocal of that, of this. So 2 becomes the numerator, square root of 3 becomes the denominator, cancel those out, and I get 1 over the square root of 3. And I can multiply both the numerator and the denominator by the square root of 3, and so I get square root of 3 over 3. So that's the tangent of 30 degrees. You may remember, the sequence is for sine is 0, 1/2, square root of 2 over 2, square root of 3 over 2, and 1. So that's the sine. Cosine is 1, just the opposite. So we start here and go the opposite way. So if you know sine, you know cosine. And then the tangent, you just take the ratio of these two. This divided by that is 0. This divided by that turns out to be the square root of 3 over 3. This is 1 because it's the same number. This divided by that is 1. And here you end up getting the square root of 3, and then infinity, because you divide 1 by 0, which is infinity or undefined. Okay, so if you wanted to use the unit circle, that's what we do. So now we can plug in. So you get 3960 times negative 1 over 1/2 times 1 over the tangent, which would be the square root of 3 over 3. And so let's do it again. So 3960, and you can plug it into your calculator at this point if you wanted to, but I'm just going to show you how this works. So 1 divided by 1/2 is 2. And here it's going to be 3 divided by the square root of 3. So what I do is when this goes to the numerator, I switch. When this part goes to up here, I switch the numerator to the denominator. So ultimately, if I multiply out the numerator, I get 3960 times 6 divided by the square root of 3, which is negative 13,700. And the units are going to be, so this is in radians, I'm pretty sure. Oh, rate of change in H. So it's H is meters. Is it meters or miles? Miles per, I guess it's an angle, actually, degrees, because it's, so the miles per degree. Okay, so is that right? Let's check the answer book. Which wish I had one of those. 92. So they've got negative 7,920. So 7,920 times the square root Oh, they're saying miles per radian. So let me multiply that by the square root of 3. So we get 13,700. Okay, so that's correct. Now, why is it radians? Well, that equals 30. Yeah, pretty much the reason it is because in calculus we always deal with the radians. So the actual angle theta is pi over 6 in terms of radians. So this has to be radians. Okay. So we converted our 30 degrees to radians and everything is right. So we'll say per radian. Okay, so where are we here? I'm trying to find my cursor. So 93 is actually a higher order derivative, so it's pretty straightforward. We just take the original function, which is 4x to the 3/2, and we take the first derivative, so we have 1 prime. So we have 4 constant times the derivative of this, which is 3/2 x to the 1/2 power. Okay, we take the exponent down, reduce the exponent by 1. So let's go ahead and simplify that before we take the next derivative. 4 divided by 2 is 2. 2 times 3 is 6, so we get 6x to the 1/2 power. So now we take the second derivative, and so we just take the derivative of the first derivative. So then we can look at this expression. We have constant times the exponent, which is 1/2, times x to the 1/2 minus 1 power, which is negative 1/2. So that's the second derivative. 6 divided by 2 is 3. I'm going to change this to 1 over the square root of x. How did that happen? Well, I can move that to the denominator. So it'll be x, 1 over x to the 1/2, and x to the 1/2 is the square root. So ultimately, the final nicest looking answer is 3 divided by the square root of x. Number 97. So another second derivative. So the first derivative is easy. It's just the constant 3 times the derivative of the sine, which we know to be the cosine. And then we take the second derivative. So we still have the constant 3. The derivative of the cosine is negative the sine of x. So you get negative 3 sine of x. So that's one interesting thing about cosine of trig functions is that you kind of go through, you come back to the original function after you take 2 derivatives, but you get a sign change. Okay, and the last problem is 118. Says the figure shows the graphs of position, velocity, and acceleration functions of the particle. Copy the graph of the function shown. Identify each graph. Explain your reasoning. So, we've got displacement or position. It's a function of time. We have the velocity as a function of time. We have the acceleration as a function of time. And we know that dx dt is equal to the velocity. And we know that d squared x dt, the second derivative of the displacement, is the acceleration. And we have 3 curves. We have one curve is a cubic, and we have one equation that is a quadratic, and one equation that's linear. So this would be like x cubed, and this would be like x squared, and this would be x. That would be the kind of equation that you'd have. And you might have some extra terms which would make it so that it intersects the x-axis at different locations than 0, but this would be the general form. And so we know that the derivative of x cubed is going to be equal to 3x squared, and we know the derivative of 3x squared, if we take the second derivative, is going to be x, or it's going to be 6x. So there's x, and there's x squared, and there's x squared, and there's x cubed. So basically what we can, if we plotted all those separately, so we've got the third order equation that looks something like that, and we got the second order equation that looks something like, so it goes down here and up like that. And we have the linear equation that looks something like, where this is 0, it goes through like that. So the most complicated one is the position. So this would be x as a function of time. This would be the derivative, v as a function of time. And this would be a as a function of time. Because of the way these things are related, terms of the derivatives. Just the general shape of the curves. So that's it. Oh, what's the second question? On your end, identify when this particle speeds up, when it slows down. Okay, so speeding up is when the velocity is increasing. And so if you look at your velocity curve here, here it's slowing down, and then it goes through minimum, and then it speeds up. So actually what happens here is it stops, then it actually goes backwards, and then it starts going forward again at this point. So this is backwards. So it's kind of like, if we kind of draw a little graph here, this is x, and this is distance. So it goes, it speeds up, and then at this point is right there. So the velocity, so it speeds up, and then it slows. It actually goes negative. So at this point, it actually goes backwards. So it goes forward, then it goes backwards. That's what's happening here. And it goes back to the original point, and then it goes the other direction and goes like that. So it's kind of like goes up to one point, comes back, and then goes through that point again. So this point is where it starts. Here is where it comes back to the original starting point, and here's where it speeds up. And during part of that, where it's negative, is where it's going backwards. And then here, this point is 0 velocity. So it's stopped, and then it goes the other direction. So during this part we're going forward, this part we're going backward, this part we're going forward.